Excellent. Thank you, Josh. All right. Well, good morning, everyone. I'm really pleased to join you and thrilled to share some perspectives that we have at PNNL on meeting some goals that we've set that are quite ambitious for 2030. So that's 3 billion gallons and then 35 billion gallons by 2050. Let's see, make the slides go. So for today, I'm going to go really quickly over what PNNL does and who we are and any capabilities that are relevant to sustainable aviation fuels research, development, and deployment. I'm going to go over those slides really quickly. They can be a little bit dense, but they're mostly there for your information. So anything I don't cover and you see online after that you're interested in, please don't hesitate to reach out to me. And then I'm going to dive into it's time to get serious about how we get to 3 billion gallons in 2030. And I'm going to make an argument that some of the ways that we approach this at the national labs is not conducive to meeting that goal. And then I'm going to offer a potential solution to making sure that we can meet our goal, as ambitious as it is. And then I'll get into some of the newer R&D that we're doing, which will be important, I think, for meeting our 2050 target of 35 billion gallons. This will mostly involve improvements to sustainable aviation fuel composition and also trying to improve carbon, energy, and hydrogen efficiencies. And then I will close with an idea that most of you are probably familiar with, but it's really a need to cross-cut sectors in order to further draw carbon down. So at PNNL, our mission is technology transfer. And so we are not able to commercialize technologies, but we do work closely with our industrial partners to make sure that we create a minimum viable product and work with them through to commercialization. So here's a quick look at who we are and what we do. We are an Office of Science National Laboratory. And so that means that we are able to do work in a lot of different spaces. That makes us quite diverse. So you'll see the portfolio here. Some of it's in basic energy science and basic energy research, but a significant chunk is in energy and environment, where I sit, as well as national security and national security related work. In the Energy and Environment Directorate, where I sit, we have approximately 1,300 staff. So just for perspective, the lab comprises about 5,000 staff in total. And more than 230 of us actually support the national security mission. So we do have several campuses in Washington State, as well as Washington, D.C., Maryland, and Portland. And the Energy and Environment Directorate objectives include decarbonizing end uses, sustainable manufacturing pathways to enable a net zero economy, ocean innovation for energy and climate, as well as nuclear materials performance, multi-scale integration of power grid and environmental systems, as well as CO2 removal use and sequestration. Within PNNL, because we are able to cross both pure science and applied science, we are able to host the Institute for Integrated Catalysis, which is the largest non-industrial catalysis or R&D organization in the United States. So PCSD brings in our basic energy science programs, and then they cross-pollinate with us in the Energy and Environment Directorate to do advanced characterization methods for catalysis, and then to bring the catalyst that we develop through to an applied application. We do have a user facility called the Environmental Molecular Sciences Laboratory. And I'm not going to go through all the super cool toys that we have here, but if you're interested in any of these, please let me know. We do have amazing capabilities in this user facility, and you're welcome to come see them and also to use them. Between the Washington State University and the Pacific Northwest National Lab, we have what we call the Bioproducts Institute. And this institute is really focused on developing science and technology to use renewable carbon and also provide environmental services. So you can see here that the vision is to be the portal to multidisciplinary research and education for carbon recycling and management. Under that vision, we host a bunch of scientists from the university as well as the lab that comprise economics, environmental science, business, chemical engineering, as well as fungal biotechnology and other capabilities that can bring diverse teams together to really look at a problem, try and figure out what we're really trying to solve, and then create solutions, usually for things that are in the environment that represent an ecological, social, or economic liability. And the idea there is if you can solve that problem, you have an impetus for commercializing a technology that solves more than one problem at one time. Within the Bessel building, so the Bioproduct Sciences and Engineering Laboratory, where most of the people in my group sit, we have a high throughput center that is used to accelerate early and mid-stage R&D by having automated material handling that can use robots to basically formulate and synthesize our catalysts, and then use a lot of data and analytics to create basically spatial maps or maps that tell us where the catalyst formulations are most effective. And then we can dive in deeper and go into larger scales. When we go into larger scales, we really focus on the correct scale as well as the geometry. This is really important because oftentimes at national labs and in academia, you see scale-up approaches that really are just making something larger. And that is not how you want to scale up a process, because it doesn't get you to a path to commercialization. And so we use fundamental principles. We use kinetics and transport phenomena to really dive into what a reactor geometry needs to look like to manage heat, as well as those transport phenomena, and leverage that to make sure that we're creating the chemistry cascades that we wish to achieve and accomplish. And so you'll see this at different scales, from very small, so about 1.4 milliliter beds, all the way up through a liter. And then we also have a unique system for transforming wet waste materials into what we call a biocrude. And that's done via hydrothermal liquefaction. And that's the funny little picture down on the bottom right that looks like it's coming through a fisheye lens. When I think about models, one way to look at this is that you have different scales. So this particular type of modeling is integrating spatiotemporal data with biophysical and geospatial models to quantify resources, to look at supply chain logistics, and also impacts. And so you can see the different layers that are in these models on the right-hand side and the bullets there. But what you can use this to do is look at site selection and resources. So if you want to put a plant, say a SAF production plant, in a given location, do you have access to the appropriate electricity? Do you have access to water and biomass resources or waste resources? Do you have access to market, roads? And so there's also weather. So when we look at this in terms of algae as an example, we worked with an industrial colleague to say, okay, well, you can grow algae, and it makes sense that a lot of it appears in the Gulf region and the Southeast and maybe the Southwest. And they looked at those locations, and some of them, they said, no, we're not going to build there because the risk of getting taken out by weather event is too high. And so you can look at all of these trade-offs and really get a sense for, at a high resolution, what you can do at a given location. When you get a little bit larger in scale, then you go to the refinery itself. And we use techno-economic and life cycle assessment to drive all of our research. Sorry, I keep getting messages. These are very important for identifying where the gaps are and how the gaps will impact your bottom line. So this is pretty standard. We do flow sheeting in ChemCAD or Aspen Plus. We then use a spreadsheet to do a discounted cash flow analysis. From there, you can pull out the life cycle inventory, and we often give that to Argonne, who builds out these conversion models in GREET, and then gives you a carbon intensity or GHG reduction potential for a given pathway, if you will. We can also use this method to do multivariate and sensitivity analysis. So getting even larger in scale and also temporally, then you have the Global Change Analysis Model, or GCAM, and PNNL is home to GCAM. This is a model where you can ask questions about how what you're doing will impact the sea level, the carbon dioxide in the atmosphere. And this is a model where you want to ask policy questions and look at the globe. So it's a great tool for getting that greater perspective, longer time scale, and it's often used to assess climate change and our progress toward putting a dent in that. So just a real quick slide here. I'm not going to go through this in detail, but the bottom line here is we work up to the demonstrate at relevant scale and configuration. And this is really just to drive home again that we cannot commercialize technologies. We rely on our partners for that. And we continue to provide R&D support for our commercialization partners as they do go on to pilot scale testing and to demo scale testing. And hopefully we'll still be with them while they're doing commercial scale work and moving on to improving their processes even further. All right, so brass tacks, how do we build out 3 billion gallons of SAF production capacity to meet the 2030 goal? Apologies, phone call, sorry. So this is kind of a stark picture here. I looked at the RINs that were generated in 2021, and some people will say this was a COVID time. I would argue that the numbers aren't all that different given the order of magnitude. So the bottom line here is that 0.03% of what we produced in terms of renewable fuels was renewable jet. And so we have some work to do. Aviation is an important market for DOE in that it's large enough for DOE to be interested in it. The small consumer set means that you were selling to airlines and consortia, so instead of maybe hundreds of thousands of gas stations. And they're pretty much just Jet A and Jet A1. And so it's a simpler type of market to try and enter into. And it's also one that's difficult to decarbonize or electrify. So it's an important market, I think, for us to be working in. And one thing to consider here as well, and you all know this very, very well, is that fuel has to meet functional requirements, and that is the foundation for an aircraft certification. And so the jet formulation and production must be carefully controlled to get the right fit for purpose and right fit for use properties. Apologies. So by first understanding the critical fuel properties, then we can focus on making a better product. And so just a high level, and most of you know this already, you want to be able to reduce soot, so we want to limit aromatic content in sulfur. We want to have high energy density. We want to maintain low temperature fluidity. So you want to be able to control the level of branching in alkanes. Too much branching is not good. Not enough branching is not good either. You want to be able to have a significant thermal stability, which means that you don't want to have any metals or heteroatoms. No olefins, which could react, form gum or break down. And you also want to be able to maintain seal swell properties, especially in the existing fleet. So what we're doing here, I'll get into later, but certain substituted cycloalkanes may assist with reducing the need for aromatics to maintain the seal swell properties that you're desiring. So one example of how we targeted a high quality fuel is the one we've done with LanzaTech, and many of you are familiar with this as well. And the key here was really controlled oligomerization of the alcohol-derived olefins into a very high isoparaffin content fuel. So basically 98% isoalkanes, and the yield is also high. So that was another feature that made us follow this technological pathway, or this catalysis route, if you will. The high yield is super important if you don't want to have to deal with the lighter than jet and the heavier than jet. There is some of that, and there are things that we can do with it, and I'm happy to talk with people offline about what you can do with those streams. You also want to minimize your hydrogen demand, and so one thing that's really interesting about this route is when you dehydrate ethanol, you lose an oxygen, but you don't have to use hydrogen to do it. And then when you get into the actual jet fuel range, there's only one double bond in the oligomer, and so that reduces your hydrogen demand. And PNNL and LanzaTech did win a Federal Laboratory Consortium Award for Excellence in Technology Transfer for this particular technology. And LanzaTech is now working on a demo facility in Soperton, Georgia, to scale up and produce jet fuel using this route. So there are many other carbon sources in this world, and we often think about CO2 and converting that. But I'm going to argue that there are several other sources that are significant and are also a problem, but they also contain energy, which makes them far more interesting for us to work with, at least in the nearer term. So by solving another problem, so if something represents an ecological liability, an economic or a social liability, we can solve that problem by creating a revenue source out of that liability. And some of the examples shown here are steel mill off-gas, sewage sludge, manures, municipal solid waste. The other advantage here is that these are cost-advantaged feedstocks, at least until they become some sort of a commodity. But they are stranded, and so they can be sort of viewed as niche opportunities. I'm going to argue that there are ways to blend them and leverage as much of them as possible. But first, you kind of want to know how much is out there. So the amount of stranded energy-rich carbon sources is not trivial. So approximately 7.5 exajoules in terms of energy content. And this does not include the conversion process itself. This is just the energy content in those materials that is out there. And then what you get out in terms of a fuel would depend on the efficiency of the process that you use. Hydrothermal liquefaction is something that many of you are familiar with as a core competency at PNNL. This is a way that we convert wet carbon streams into what we call a biocrude oil. It's basically pressure cooking. It's using heat and water and pressure to convert the solids in a slurry or a wet waste stream into a biocrude liquid, which is basically a complex liquid. But there are other streams that come off of this, including an aqueous stream and a solid stream and a gaseous stream. The solid stream is interesting because you can recover nutrients such as phosphorus and nitrogen. The aqueous stream contains carbon, and we're looking at ways to pull the carbon out of it and make it useful. And then the gaseous stream can be further utilized as well. There we go. So the reason why HTL is really interesting to me is because it expands our feedstock base from what we consider classical biomass, so terrestrial and forestry biomass, to low-cost carbon waste streams such as municipal wastewater sludge, food waste, manures, and more. We're also looking at waste carbon streams such as CO and CO2, and these can come from many different places. So what's shown on the slide here, which you may have seen John Holliday present before, you have CO2 point sources. And then there are industrial waste gas streams, such as those from refineries or steel mill off-gas or other manufacturing, gas flaring. There's also biomass gasification that can produce a synthesis gas. And from here, we know how to ferment the synthesis gas, or at least LanzaTech does, and then the catalytic step after that, or catalytic steps, manipulate those chemical bonds and convert those carbons and hydrogens into synthetic jet fuel. And so here's just another look at how you get CO-rich gas. This is from steel manufacturing, and this is something that LanzaTech does very, very well. So landfill gas is really interesting to me because it comprises CO2 and methane. And so if you can incorporate that CO2 into your product stream, you can utilize CO2 without having to use an electrolyzer and the grid. And so that is really interesting to me, but that doesn't mean that it doesn't come with challenges. So landfill gas can have hundreds of contaminants in it at very small quantities. And oftentimes the approach to that is removing them. And because the strategies for removing each contaminant is kind of specific to each contaminant, there's often a series of sequential steps in order to remove each of the contaminants and then CO2. So there's a need, I think, to work at strategies that can avoid all of these sequential removal strategies and incorporate the CO2 into the product stream. Other challenges that are sort of less discussed are the difference between plant life, which might be 30 years, and the landfill ability to provide the landfill gas. So that's something that I'd be interested in talking with people with and learning more about if anyone is interested in that. But I see this as a way to get inexpensive synthesis gas, which I'm going to argue is very important for getting to that first 3 billion gallons. In addition to what's in landfills, we also have these wet waste. So fats, oils, and greases are limited. We are seeing that converted into HEFA today, as well as renewable diesel. And there's a need to have more feedstocks because we can't replace all of the demand with the amounts of fats, oils, and greases that are produced on the planet today. So what else is out there? There's sludges, manures, food waste. And what's really interesting when you look into this analysis is that 80% of the non-sludge waste occurs within 25 miles of a wastewater resource recovery facility that is greater than 1 million gallons per day. This means that you could host an HTL facility, as an example, and at a wastewater recovery facility, and bring in all of these other stranded carbon assets and achieve not only economies of scale for the HTL plant, but you can also process these additional wastes and reduce the economic and ecological and social liabilities associated with those as well by converting them into a fuel product. Municipal solid waste is a little bit harder. It's a solid. And so this has presented many challenges over time for gasification in terms of feeding. So feeding the gasifier is really challenging. I'm also going to argue that we've been looking at the incorrect configurations for gasifiers, at least in the bioenergy world. One thing that we do need to look at in terms of MSW is there are inherently unrecyclable materials that have attractive heating value, but they're not considered in RINs or LCFS credit schemes. This is something that we need to work with policymakers on. Plastic, as an example, is not infinitely recyclable. Once it meets that end of life, we should be able to reap the benefits of the high energy density of that material. There's also a lot of poor public perception in terms of gasification. You might remember some of the campaigns by the Sierra Club in California years ago, calling them incinerators in disguise. But I think that gasification is really a great opportunity for us, and also would argue that MSW hotspots align well with locations of sustainable aviation fuel consumption that we would project ahead. If you look at this from, this is a AIDA, I think, report. The source is down here on the bottom, and you can go look at it. But if you crunch these numbers, 65% of projected SAF demand could be met by combining a syngas platform with cost-advantaged feedstocks. And these cost-advantaged feedstocks are shown on the left. They're circled by the blue dashed bar. So MSW, forestry waste, wood processing waste, ag waste, industrial off-gases, and then all of the other ones that I showed you above before that aren't necessarily captured by this particular study. Let's talk about gasification and where the Bioenergy Technologies Office has been. So way back when it was the Industrial Technologies Program, and also when it was the Office of Biomass Programs, DOE focused on a single molecule, ethanol. And at the time, the national labs had a syngas simulator and a sort of entrained flow type of gasifier. And the materials of construction limited this gasifier to 700 degrees C, which means that we basically had tar generators. And so most of the program for many, many years was focused on tar reforming and also synthesis of mixed alcohols, which is interesting, but hasn't really led to cellulosic ethanol from a thermochemical facility. In addition to that, our analysis efforts were always tied to 2,000 dry metric tons per day in terms of a plant scale. So in 2005, we did the design case to make mixed alcohols using gasification. And in 2012, we validated that. NREL did a terrific job of showing that we could do this for a long time on stream and make significant quantities of mixed alcohols. But we were still focused on a single molecule. We had some work in pyrolysis, looking ahead toward needing hydrocarbons, but still the office was mostly focused on ethanol. And that's where Congress and DOE was at the time, and that's where we all were. Again, gasification work was focused on tar reforming and mixed alcohol synthesis. And then in 2013, we got smacked in the face with this transition that we had to make. So we showed ethanol was viable. Now what do? We had to make hydrocarbons. And so the office made a shift in 2013. Gasification work was largely eliminated apart from some of the integrated biorefineries. And then our efforts shifted from the actual gasification, which I would argue we never really did much of, to upgrading of higher alcohols, and then today also working with C1 chemistry. So transitioning from wet wastes to more complex solid waste, which we need. So I said there was a significant amount of wet waste, but there's also not enough to meet demand. So we need solid waste, and we need lignocellulosic material. This gives us cause to rethink gasification and gasifier configurations. So I'm going to argue that there are two strategies here. One is destruction, and the other is high efficiency. When it comes to municipal solid waste, there are hazardous materials in there. You don't want to touch it. There's biomedical waste, and then there's also the potential for landfill mining. In that particular case, we want to use one gasifier configuration. And then in the other, I think we want to leverage what we already know how to do, which is make these complex liquids using fast pyrolysis and hydrothermal liquefaction. Let's incorporate CO2 as an oxidant. And then there's some work at WSU that I'm going to share with you about carbonization to more uniform and concentrated carbon to feed into a gasifier. So this first example is a gasifier by a company called Inintech. They're actually a spin out from PNNL and MIT. And what they do is they use a downdraft gasifier. So you are inhibiting your ability to have complete conversion of the carbon because of the length of the gasifier. But what you're doing is you're taking anything that doesn't gasify and you're rendering it inert in a glass formulation or some other formulation so that you can incorporate it into the built environment. And so you take that hit in yield, but you're solving another problem. And so there's some research needs that have to go on to make this deployable largely and nationwide. So I'd be really interested in talking with people that have some areas of interest here under the research needs, as well as any capabilities that can bring to bear to solve some of these research needs. And then here's the carbonized biomass. This is work done by Dr. Manuel Garcia Perez at Washington State University, where he uses an acid and pressure to minimize the amount of volatiles that come off of the biomass as you sort of torrefy it and make it into a pellet that you can then use for gasification. And the idea here is to preserve carbon and potentially use CO2 as an oxidant to increase the carbon that's actually going into the system and then going into your product. And the third example is something that I've been thinking about a lot lately. So we know how to do fast pyrolysis, catalytic fast pyrolysis, HTL, and we get these really complex liquids. And our inclination today is to throw a catalyst and hydrogen at it and hydroprocess it to remove metals and heteroatoms. The problem here is that we produce fuels with lower yield to SAF. So in the case of hydrothermal liquefaction, if you just go straight without cracking the heavies, maybe 23% yield in the jet range. So why would we continue to force fit what we're doing into a SAF paradigm when we could greatly simplify the system? We know how to work with gases. We could use these complex liquids as a liquid format feedstock to overcome the solids handling challenges with gasification. And then we know how to work with synthesis gas. From there, you can get to anything, including and especially SAF. And the last final example here is our newest project with Sky Energy Americas and Lonza Tech, as well as Linde, Argonne, and Energy Vision. This is called Project Lotus, and it's basically using landfill off-gas to make ultra low carbon intensity sustainable aviation fuel. And the objective here is to construct and operate the very first landfill gas to sustainable aviation fuel commercial demonstration facility, and I'm super excited about it. We will be starting phase 1 very, very soon, and phase 2 will be construction. So I hope to give you some updates on that, and I'm sure you'll hear about that from John Plaza at Sky Energy Americas, as well as our friends at Lonza Tech. Okay, so to meet the 2030 goal, we need to simplify wherever possible. The routes from syngas can leverage existing ASTM pathways. It took us 8 years to get from bench to ASTM approval. We only have 8 years to build out 3 billion gallons. We need to leverage the existing ASTM pathways. Let's use what we've learned from fast pyrolysis and HTL and reconsider gasifier configurations as well as feedstock formats. And there's more out there. There's autothermal reforming, there's partial oxidation. There are so many different ways to get to syngas. Let's discover new routes to cheap syngas together and then leverage a back end that we understand and build out 3 billion gallons. Okay, so to 35 billion gallons. What can we do from here? If I was a company, I would probably be building out and commercializing what I had in hand. And then I'd be making little improvements. So what improvements can we make? We can make improvements to composition, as well as carbon energy and hydrogen efficiencies. So some of the newer work at PNNL being done by Rob and Vanessa Daigle here is ethanol to butenes. This enables a new chemical and jet pathway, and it's also a process intensification strategy because it eliminates the ethanol dehydration unit. And in doing so, you avoid capital. You also combine an endothermic and exothermic reactions, which reduces your energy intensity. And you can also make co-products if that's something that your enterprise would like to do. And if you'd like to know more about this, I'm happy to connect you with Rob and Vanessa Daigle. Please let me know. More on process intensification, also from Rob Daigle. This is using the microchannel reactors that we developed to apply to reactive separations. So basically what we're doing is we're combining the ethanol and water separation, as well as the reactivity in a single unit operation. This one is also modular, so it's interesting in multiple perspectives. When you think about modularity, the idea here is that you can achieve economies of mass production as opposed to economies of scale. And this particular technology has been applied to Fischer-Tropsch. It's been applied to a bunch of different chemistries. But what's really cool is that it 3 stages of separation with 10 times of reduction in the height equivalent to the theoretical plate versus conventional distillation. So that's a huge energy savings. And then it has 85% yield to ethylene at modest pressure and a relatively strong weight-hourly space velocity. This work is being done by Karthi Ramasamy here at PNNL, and what he's doing here is he's targeting reduced aromatics. He's also trying to reduce hydrogen and energy intensity by using ethanol-rich oxygenate streams to form ketones and then do ketone condensation. And the idea here is to make mostly substituted cycloalkanes, but also isoalkanes. And one thing that we have to prove, but is theoretically possible here, is that hydrogen generated from the ethanol to ketone steps could potentially meet the requirements of the overall process. So that's how he's reducing the hydrogen intensity. And then because you can process wet ethanol with minor impurities, you're reducing the process severity and thereby reducing the energy intensity required. Here, everything but the neat fuel basically meets all of the key requirements for sustainable aviation fuel according to tier alpha and beta tests. And then the yield setting index for this is almost 50% lower compared to conventional fuel. So this is showing how cycloalkanes can become a strong component of the sustainable aviation fuel, reducing the need for aromatics, and also in doing so, reducing the amount of soot that is formed while generating it. This is a slide that you may have seen presented by John Holliday. This is showing how ethanol plants can provide a CO2 point source that can potentially make up to 4 billion gallons of fuel. And this analysis was performed by John and also Michael Kentner-Meyer and Bob Weber at PNNL. And the analysis was really interesting because what it showed was that the electricity demand here is huge. This is not a curtailed electricity strategy. This is not a way to use, cheap renewable electrons. We really need to be careful when we think about power to liquids and how much energy it really, really takes. And with that, I'll just jump to something out of our fossil energy and carbon management sector, where we're integrating CO2 capture and conversion to reduce the overall energy required for conversion by activating the CO2 in the solution and doing the conversion there. And if you'd like to know more about this, I'm happy to connect you with that sector of the lab, as well as Dave Hildebrandt and others that are working in this space. And finally, we need to be collaborating with other sectors, and in particular, the ag sector. Natural climate solutions are low tech. They can be deployed today. What's stopping us? We can reduce 1/3 of what we produce in terms of greenhouse gases every year just by using the soil and earth that we live on. And so what aviation can do here, as you well know, is you can subsidize regenerative farming by helping farmers buy equipment, sensors, and using digitalization, implementing seasonal monitoring using planes and drones and satellites, by providing seeds and other things for cover crops, by resolving hyperspectral satellite imagery and having continuous monitoring of soil organic carbon, water content, nutrient content, and also help to support energy crops that we would then turn around and use for sustainable aviation fuel. And with that, I'm going to say thank you very much and let Josh go into questions if there are any.
Thank you very much, Corinne. I'm going to try something a little bit different today. I do have a list of questions, so I'm going to go through those first in the more or less in the order that they were asked. But at the end, I'm going to try and let people raise their hand. And so if you're looking at your Zoom screen, go reactions, raise hand, and you can ask questions directly after we get through these initial Q&A that people have submitted. So Corinne, there's a question I got directly from an audience member. You talked about syngas production as, how can we make as much syngas? And there may have been a misunderstanding, but are you proposing using bio oil and then gasifying it to a syngas for FT, or is that part of your matrix for SAF?
I am advocating that we take those complex liquids and we simplify them by converting them into syngas. I would not recommend FT, but more power to you if that's what you want to do. There are ways to use catalysis as well as biology to turn that synthesis gas into an ethanol or a methanol and go from there to make SAF.
Thank you. Another general query from the audience is how much opportunity is there for other agencies to request PNNL to do work in a specific area or assist a specific sector? If you have a lead-in at PNNL or contact you.
How much opportunity? Give me a call. Send me an email. My email address is on the title slide. And I welcome any discussion and inquiry about what we can do. There are several sectors at PNNL that might be of interest to you, and so I can connect you with the appropriate people if I don't know how to do it already myself.
Thank you. Can you comment on the lack of air? I believe this question is about the lack of aromatics in the liquid fuel, not necessarily in regards to NBPM, but is there any health impact, I guess, from paraffinics with a lack of aromatics in liquid fuel? Has there been any work done on that?
I don't know how much work there's been done on the health effects. I would love to see somebody do the life cycle impact analysis called Recipe 2016 on this, where it basically looks at 17 different modes that impact human health, ecological health, and resource health. And it has sort of proxy molecules that you can use to quantify the amount of health impacts on those three systems. But no, I'm not aware of anything related to paraffins and health. And I would love to, if anyone else knows, to see that data.
Yeah, if I may jump in just to remind everybody that paraffinic fuels, whatever is in that fuel is already in the jet fuel. So you're just taking out the aromatic portion and replacing it, whatever is already in the jet fuel.
Right.
And aromatics, not necessarily in their liquid product form, but they are associated with higher NBPM and soot emissions as well in the combustor. So removing them helps with NBPM and soot reduction.
Right. I think the question is, can we get below the magic number, which is what, 8% aromatics that we want in there? So
8.4.
I don't know yet.
Yep. Do you use a catalyst in the HTL process?
We don't use a catalyst in the HTL process itself. We have in the past, and we have the ability to if you wish to run tests in that kind of a configuration. But no, we generally do not practice with catalysts in HTL until we get to the upgrading part, which is where we do the hydroprocessing to get to a hydrocarbon.
And can you talk about the type of products that come out of the HTL process in terms of the relative fraction for gasoline, diesel, jet, or otherwise?
It's primarily diesel. I don't want to quote, but I'm going to say upwards of 50–60% of it's probably in the diesel range. So there are others on the call that may be able to answer that, and I can also get back to you if you send me a message. But mostly it's diesel.
Considering the high moisture and oxygen content of raw biomass, couldn't we greatly increase the total energy content of the fuel products by adding renewable processes like heat and green hydrogen?
Yeah, that's definitely a Paul Bryan question. I would agree. I think that we do need to be able to make green hydrogen. And one of the things that we need to get to that 3 billion gallons that nobody talks about, we need a hydrogen infrastructure. Every path that you take to SAF requires hydrogen. So we need that hydrogen infrastructure, and a green hydrogen infrastructure would be terrific.
Excellent. Can you comment on, there's just a general statement about forest residues and how there are many of them at the moment. I don't know if you could make a comment about your perspective on forest residues and
absolutely
in terms of removing them from the environment and using them for SAF.
Right. So this is a great opportunity. And so this material is really difficult to access. In many cases, there are no roads. In many cases, you can't get large equipment in there. This is an opportunity to build mobile pyrolysis or other types of units to make a liquid that you could then transport to a larger facility and use an in-train flow gasifier as an example, the most efficient gasifier we know, and take that complex liquid, make it simple, make it gas, make it into SAF. And so, yeah, I would advocate for mobile pyrolysis units. Absolutely.
Excellent. Another comment I got, a question I got directly in the chat is about methanol as an ATJ feedstock. And I know this has come up with a lot of different producers, trying to get methanol and other alcohols into the specs. I don't know if you can comment, is PNNL working on this or thinking about this? And
so we are working on methanol to SAF. I think that it's interesting from a catalysis perspective, but it's not covered under the ASTM annex for alcohols. So there's going to be a lift there to get it through.
There is another general, maybe Peter or someone else could paste. Corinne, you wouldn't mind if we share your email in the chat directly?
Not at all.
So if maybe Peter or Gerhan could share Corinne's email in the chat. There's a request for that. Let's see here. For the for slide 21, for the PNNL LanzaTech ATJ process, how much in gallons, being jet fuel, is produced per gallon of ethanol? If you're able to share that.
21. I don't have that number off the top of my head. I'm so sorry. I will say that the catalysis part of it is incredibly efficient, and 90% of the carbon, or upwards of 90% of the carbon, goes into the SAF.
Going back to the hydrogen comment you made before, could you elaborate on why hydrogen infrastructure is needed?
Oh, yeah. So if you think about it in terms of of HEFA, those are fatty acids. So you have to eliminate the double bond, and you have to also get rid of the oxygen. So you need hydrogen to do that. When you make a SAF, when we oligomerize alcohols, we wind up with a single olefin or a single double bond at the end. So you need hydrogen for that. So every one of these, when you start with biomass, you have to remember that there's oxygen present. And so there are a couple ways to get rid of it. You can dehydrate, you can throw hydrogen at it and lose it as water. Every pathway that you use, the chemistry requires you to do at least a final hydrogenation, if not saturation of double bonds, as well as elimination of heteroatoms. Every process requires hydrogen. So yes, we need a hydrogen infrastructure.
Going back to the HTL comment you made about a large fraction of it being diesel, about how, what's the maximum fraction you could increase the HTL to jet, and what are kind of the cost drivers or effects you have when you drive to more jet?
So right now, you could get approximately 20 to 23% of it in the jet range. What you would have to do to get more jet is you would have to crack the heavier than jet, which I would argue we need to learn how to control that. And it requires more hydrogen and an additional hydrocracker. So that's additional capital.
Thank you very much. There's a comment about how do the SAF feedstock supply projections for 2050 account for the competition with R&D, renewable diesel, excuse me. How do the 2050 projections account for renewable diesel, which is cheaper to produce and can be sold at a higher premium?
How do the targets account for that?
How do the feedstock supply projections?
Feedstock supply. So this is an interesting and really fundamental question. And the strategic analysis arm at DOE is looking into this. They recently had a lab call where they're looking at, okay, we have a constrained amount of material. What can we do with it? And then what should we do with it? And how do we prioritize? So I think that companies are going to do what's best for their enterprise in terms of economics, and the rest we're going to have to figure out. DOE projects that there's potentially 1 billion tons of biomass. We have yet to see that. But I think we need to figure out if that's the potential, how do we get there?
All right, we have, oh, I did see someone raise their hand and now it's down, and I did see a question from them earlier. Now I'm going to try and find that question now that I don't see their hand raised. Danielle. Are you aware of any commercial processes available right now to upgrade biomethanol directly to SAF? So,
well, there's methanol to olefins, and you can take those to gasoline, and you could potentially get them larger, make them larger. So, but commercially practiced, I'm not aware of any. I could be wrong though.
All right, we do have someone raise their hand here. You'll have to unmute yourself officially, but I believe you can speak now.
Thank you, Josh. I have a question regarding the scale up of the sustainable aviation fuel processes technologies. I was wondering, is there any? Do you have any comments about the scale up methodology, as well as if there are any technical reports from PNNL or published papers that I can refer to regarding the scale up process?
So it's going to depend on what scales you're talking about. When we get to sort of engineering scale, I can walk you through those steps from bench to engineering scale. When it gets to larger and larger scale, NREL did some work there. They recently published, I want to say in a Chemical and Engineering News, an article about scaling up for a plant. Zeton puts out a lot of publications on how to scale up. So do other engineering and EPC firms. But let me think about that and send me a note. I will look for some papers, both from PNNL and from others to help with that question.
There's also a comment about PNNL using GREET for LCA.
Yeah. So GREET is something that belongs to Argonne, and what they do is they take the life cycle inventories that come out of labs like NREL and PNNL, where we do the conversion process simulations, and they incorporate those life cycle inventories into the GREET model, which then comprises from the ground to the actual end of use. So we contribute to GREET. We sometimes use GREET. But there are other methodologies out there as well that we like to look at and compare contrast, because they both have advantages and disadvantages, of course. All models are wrong. Hopefully some of them are helpful.
One of my favorite quotes as well. We have another question from a raised hand. So you should be able to unmute yourself now.
Yeah, thanks, Josh. And thanks, Corinne, for the presentation. I had a question. So you mentioned a couple of processes in your presentation, HDL, HEFA, Fischer-Tropsch, and alcohol to jet. So would you say that one of them would be more preferred than the other in certain cases? And which processes are of current interest to generate more biojet in terms of economics and environmental perspective?
So I think that HEFA is being built out to the extent that we can with the available fat resources. The world tends to produce as much fat as we need to be healthy. And beyond that, we need to look at how do we leverage oilseed crops as cover crops, as an example, and produce more of them. So HEFA is certainly interesting. Wastes are interesting. I would not pick a winner. Even though I'm suggesting we need to pick a couple of them. So I think that HEFA, I think that the syngas fermentation and ATJ, as well as some of the other people that are making ethanol to jet, I think is going to roll out first. And we'll see what happens from there. I have the same question, I guess, that you have. And what I shared in the presentation is pretty much where I stand in terms of what I think we should do, which is a syngas platform. And from there, you can go really anywhere. And I could be biased because gasification is my domain, but I think we've been thinking about gasification wrong for decades. And we need to revisit it and look at it from a new place.
So we got a couple more minutes left here. Can you comment on the particle size that you use or need or require for HTL?
So the general rule of thumb for particle size when it comes to a system like HTL is that you want your particle diameter to be approximately 20 times less than the diameter of the pipe. So I don't give a spec on what we use because we're at bench to engineering scale. And so I don't want you to take that number and run with it like, oh, this particle has to be this much to work in an industrial setting, because in real life, the particles can be much larger than what we work with.
All right, well, I hope my accounting is correct, but I think we've answered or commented on almost everything today. So with 1 minute remaining in the call, I'd like to thank Corinne for joining us and for all of your questions here at the end. On behalf of myself and the rest of the CAAFI R&D committee, I hope to see and hear from you again. Thank you very much, Corinne.
Thank you, Corinne.